Once again, I, Ajay Jha, on behalf of ACS India team, welcome you to today's ACS Science Talk. Just to update you on the upcoming ACS Science Talks, just visit our ACS in India webpage to register for the upcoming ACS Science Talk on 28th May. We have also uploaded the past lecture recordings of the ACS Science Talks in the ACS Science Talk virtual library section. Feel free to visit, like, subscribe, and share among the scientific community. We have also an upcoming ACS India webinar on May 19th on how to start a startup by Professor Amitabh Bandyopadhyay from IIT Kanpur, who is popularly known for his 90 days streak for making a world-class ventilator. So definitely it's worth registering and having a look into this session. Then to update you on the latest science, research articles, events, updates, and product launches at ACS, we have a monthly newsletter, ACS Insights India. Subscribe today for free. We'll provide the link into the chat box during the session. Now, to begin with the scientific session, it's a pleasure and honor to have Professor Jodie Lutkenhaus with us. She is the William and Ruth Nelly Faculty Fellow and Professor in the R.T. McFerrin Department of Chemical Engineering at Texas A&M University. She received her BS in Chemical Engineering in 2002 from the University of Texas at Austin and her PhD in Chemical Engineering in 2007 from the Massachusetts Institute of Technology. Following a postdoctoral position at the University of Massachusetts, she joined the faculty at Yale in 2008. In 2010, she moved to Texas A&M University and was promoted to associate professor in 2015. Professor Lutkenhaus' current research areas include polyelectrolytes, redox-active polymers, energy storage, and anti-corrosion coatings. She is popularly known for her research on polypeptide organic radical batteries, a glimpse of which she'll be giving today. She has received recognitions including World Economic Forum Young Scientist, Kavli Fellow, NSF Career Award, Air Force Office of Scientific Research Young Investigator, 3M Non-Tenured Faculty Award, and many more. She is the first Vice Chair of the AICHE Materials Engineering and Scientific Division. Professor Lutkenhaus is the Deputy Editor of ACS Applied Polymer Materials and also serves on the editorial advisory boards for ACS Macroletters, Macromolecules, ACS Applied Nanomaterials, and other journals of international repute. Now, I would like to invite Professor Lutkenhaus to deliver her talk. Professor Lutkenhaus, please.
Thank you, Ajay, and thank you, ACS India, for inviting me to interact with you and share this work with you and to tell you more about the journal. But first, I wanted to say I've learned about the challenges that COVID has posed to your country, and my heart is very heavy for you. I hope that this hour will serve as a distraction from the situation. And when things are tough, I like to get distracted by one of my favorite things, which is science. So I hope we can share that together. Today we'll be talking about my lab's work in redox-active polymers for energy storage. But before we begin, I wanted to tell you more about ACS Applied Polymer Materials. We are a journal that is part of the ACS Applied Materials family, which includes applied energy materials, nanomaterials, biomaterials, electronic materials, and of course, ACS Applied Materials and interfaces. The journal first started in 2019, so we've been going for a couple years now. And our focus is to be the go-to forum for emergent polymer applications research. So we're really focused on the application that is enhanced or enabled by your research. Kirk Shans is the editor-in-chief. He oversees all of the applied materials journals. And then I'm the deputy editor, which means that I handle the day-to-day operations. So when you submit a manuscript to us, I'm the first person that sees it and makes some decision about it. So if you have any questions about, is my paper suitable for the journal, or you want to propose, say, like a review article, I'm the one that will be handling those decisions. And you can contact, regarding the journal, you can contact me through the editor-in-chief email. to give you a closer view of our scope, I've cut and paste some parts of the scope because people often ask us, how are you different from Macromolecules or other journals in ACS? And that can be found in the scope. We're really focused on the applied nature of the work. So you're integrating your fundamental knowledge, your fundamental studies in this multidisciplinary nature, but it's often impacting an important polymer application. So for example, we may handle some papers that are a little bit more on the fundamental side, but they have a very clear impact on application. So adhesives, epoxies, those are some examples of, there can be some fundamental studies, but the application's really clear. And then we can span all the way up to application and device where there's some less fundamental impact or fundamental attention. We're really interested in any polymer application, but I've named a few just to give you some examples. Energy storage and conversion, separations, membranes, adhesives, coatings, sensing, adaptive and reconfigurable materials, electronics, photonics, biomaterials, and composites. We've been around for a couple of years, as I said, but we've been kind of trying to highlight some of the emerging areas in polymer applications through forums and special issues. Besides our Young Investigator issue, we've done special issues or forums on gels, polymers for photothermal applications, separation membranes, and 3D printing. So we're expecting to have more coming up. What I'm doing here in the next 3 slides is I'm highlighting some work that came from our editorial advisory board members in India to give you an example of the sorts of papers that we're looking for. Rahul Mangal is one of our editorial advisory board members, and this paper discloses the fabrication and characterization of porous PTMA adhesives. So this is an example where there's some fundamental work, but the application is very clear. So I encourage you to look at these papers to give you a level of the topics that we're looking for and the quality we're looking for in our journal. This paper comes from Kana Sureshan. The title is Scalable Topochemical Synthesis of a Pseudoprotein in Aerogel for Water Capturing Applications. So this gives you an example of separations plus some synthesis. So I think it's a good example because it combines synthesis. We have a lot of synthesis papers in the journal, but they're also geared towards a certain application. And this paper comes from Menikam Jayakanan. The title is Parylene Tagged Polycaprolactone Block Copolymers and Their Enzyme Biodegradable Fluorescent Nanoassemblies for Intracellular Bioimaging in Cancer Cells. So this one as well has some synthesis, and it has some biomedical application. So in our journal, we will also handle papers that have some biomedical application. We do not require any animal studies because we're an applied polymers journal. We're not branded as a biotype journal. So cell studies are fine. Drug release is fine. We don't need an animal study in our view. Okay, so now on to the science. So I'll be spending about the next 30 minutes talking about some work coming out of our group in the general area of redox-active polymers for energy storage. So we're motivated by the idea that batteries are essential to modern life. You'll find them in portable electronics, power tools. They're growing in electrified transportation. And they're also growing in the application of grid scale and microgrid scale energy storage. And I have just a few images here to give you an idea of where batteries are used. The market for batteries is set to keep growing. The portable electronics industry seems to have plateaued. Everybody by now has a cell phone, but the largest growth is anticipated to be in electrified transportation. And this is because of many of the commitments that countries and manufacturers have made towards producing and adopting electric vehicles. And so with the growth anticipated for lithium-ion batteries or batteries in the electric vehicle market, we begin to face a supply and demand problem. So we can't make infinite lithium batteries to satisfy this insatiable market. There are limited global reserves of the constituent elements that go into batteries. And so this is going to cause our growth to be checked by the economics of supply and demand. To understand the problem, let's talk about how a lithium-ion battery works. Today's lithium-ion batteries consist of a cathode that may have any of these materials, an anode that may have graphite or be spiked with silicon oxide, and then a non-aqueous electrolyte with a lithium salt. So the key elements that have that potentially have this supply and demand issue are lithium, cobalt, and nickel. And if we look at the history of lithium-ion batteries, we'll note that their life cycle really hasn't been considered very well. Lithium-ion batteries right now are recycled in the single digits. So this is going to have immense consequences on the global materials supply and demand of those constituent elements. Another thing to note is that the fundamental chemistry of the lithium-ion battery really hasn't changed much in the last 20 to 25 years. So there's a lot of opportunity for innovation. Surprising to me, I learned recently that there are anticipated cobalt and nickel shortages in the year 2035 and 2045 if the world grows, if the world lithium-ion battery consumption grows at the current pace. So it's been discussed that the long-term lithium-ion battery price will be dominated by the cost of the cathode materials. So this provides a motivation to find some new chemistries. Another opportunity besides new chemistries would be adjusting the battery life cycle and addressing the issue of poor recycling. The problem right now is that the method of recycling lithium-ion batteries is not really settled. This graph shows 3 possible ways. There's direct recycling, hydroprocess recycling, and pyroprocess recycling. The problem is all of these recycling methods are energy intensive. So you think you may be doing the world good by recycling, but the carbon footprint of these methods can be quite large. So again, there's plenty of opportunities here for improvement. Besides material supply and recycling, there's other issues associated with safety, performance, and then the social impact in developing countries. I personally was very motivated in this area when I learned at the World Economic Forum in 2017 that a large portion of the world's cobalt is mined by children. And so I wanted to personally find other chemistries that are cobalt-free. And my background is in polymers, so I thought polymers might provide some solution to this problem. So that brings us to the idea of organic batteries. These organic batteries potentially could be metal-free. The way we would do that is we would replace the cathode and the anode with small molecules or polymers that are redox-active. And many people have been working on this for several years. And this gives us a baseline for their typical performance. So we can compare the organic battery performance to the lithium-ion battery performance. And I didn't put any numbers on this graph because I don't want you to get distracted by numbers. We just want to talk about it qualitatively at first. In terms of energy and capacity, the organic battery doesn't have values quite as high. I can point to some chemistries that have outstanding capacity for the organic battery, but then they have problems with cycle life or chemical degradation. However, the organic battery chemistry tends to have a much higher power, and this is a result of the mechanism of how energy is stored in the organic battery. The lithium-ion battery relies on intercalation, which can be diffusion limited. The organic battery, as we'll discuss, has an entirely different mechanism of energy storage, and it tends to lend you a high power. So that's an advantage. However, the organic battery is still challenged by the low cycle life. The major problem is dissolution, and we'll see that come up again and again. So dissolution continues to be a problem. However, this can be easily solved with cross-linking or by picking the proper electrolyte. It's just something the field needs to pay more attention to. Our focus here is going to be a radical-containing polymer called PTMA. This is the polymer that I feel is getting a lot of interest because it satisfies many of the challenges that we've been talking about. But it's part of a broader class of polymer that includes stable nitroxide radicals. So this polymer stores energy by the reversible oxidation and reduction of this nitroxide radical group, where I can oxidize it and take an electron away, and an anion will come in to balance the charge, and we'll call that doping. And the anion can be really any sort of anion from the electrolyte. One of the interesting features is that this has a non-conjugated backbone, so it's really different from conjugated polymers. So there's been some debate in our area about how electronically conductive are these polymers really. It's agreed that these polymers are not metallic-like, but there's been observations that these are insulating or semiconducting. The charge, this is a typo here, the charge is actually very localized on the nitroxide radical. So because you have this localized charge, it gives you different properties and a different mechanism of energy storage. As far as the polymer goes, this polymer has a half-wave redox potential of 3.6 volts versus lithium, which is quite high, a theoretical capacity of 111 milliamp hours per gram, which you can easily achieve in cycling, high coulombic efficiency, and very high cyclability. And you can get fast charge and discharge. In this graph, you can see that you can get C rates up to 50 C. And in other words, that means you can charge and discharge your battery in a minute if you like, or if you do a rate of 1 C, in an hour if you like, depends on what you're going for. So you can get very high powers. Okay, so next, I want to tell you more about this general class of polymer. These are called macromolecular radicals or radical-containing polymers. The general theme is that they have some stable radical as a functional group. I want to talk about these polymers through the context of length scale. At the smallest length scale, we can consider the switching out the redox-active functional group. I said that the nitroxide radical has a whole family, and in this graph, we're showing possible combinations of these redox functional radical groups. Depending on the one you pick, you can have a different voltage, and in turn, that'll give you a different capacity. The one I told you about is PTMA that has a tempo group hanging off, but there's certainly many more to choose from. You can also select the backbone of the polymer. The one I showed you was a polymethylacrylate polymer, but you can have a great variety of norbornenes, ether oxygen types, so many types of different backbones to choose from. And those are all going to manifest in different properties and different performance. Then in our next consideration, we need to think about how all these radical groups pack together, because their packing and their local density is going to control the performance of the battery. We also need to think about the mobility, the segmental mobility of the polymer backbone, because as you'll see, that's going to control the kinetics of the reaction. And then finally, at larger length scales, we may think about how do these radical groups arrange into larger microdomains. And I should note that in all of these polymers, they are amorphous. So there's no crystal engineering as you might have with a conjugated polymer. We need to think about these as amorphous glasses or swollen amorphous gels. So in this talk, I'm going to talk about the mechanisms of electron and ion transport. We don't have time to talk about solubility, but I invite you to ask me about that later. And then we're going to touch upon some of the latest work that came out of my group on metal-free aqueous batteries, and then the degradable polypeptide organic radical battery that came out in Nature last week. So I'll start with talking about how these polymers transport electrons and ions. I hinted that it's really different from what you've seen before. So as a platform, we're going to talk about this in the context of this polymer PTMA. And if we put PTMA in a battery in one of its first constructs in 2005, it would look like this, where the anode and the electrolyte are still the same as a regular lithium-ion battery, but we switch the cathode out with the PTMA. So as we charge and discharge it, the PTMA becomes positive, and then we're actually exchanging anions instead of lithium cations. So it's a bit different. So in that idea, we want to know, how do the electrons and ions transport in this cathode? In a collaboration led by Hiro Nishide and Kenichi Oyasu of Waseda University, we learned that electrons are hopping from radical to radical, aided by the physical diffusion of the polymer chain. So the way this works is that you have electrons hopping between sites in the chain or across chains. So we consider that to be a homogeneous electron exchange. And finally, as a last step or a first step, the electron can hop into the current collector. So we think about this in terms of two rate constants. One rate constant is the homogeneous apparent exchange constant, self-exchange constant, and the other one is the heterogeneous constant, where it crosses the boundary into the current collector. What was found was that the segmental mobility of the polymer is really key in making this happen. So we need to think about the mobility of the polymer. If you can see my hands here, my hands represent the radical groups. As the polymer wiggles around and diffuses, the radical groups can go along with that, and sometimes they get close enough to each other that an electron can transfer. So that's really important. This was determined by studying a very broad class of families of not just nitroxide radical polymers, as you can see in the top row, but also non-conjugated redox-active polymers that bear other sorts of groups like quinones and viologens. So it was found to be general for all types of these polymers. If you're interested in the math behind this, we can see how the diffusion coefficient of the polymer relates to the heterogeneous rate constant. where we can measure the diffusion rate coefficient through dynamic light scattering. We're also working on measuring it through other means currently in my lab. And then you can also see here how the diffusion rate coefficient, the diffusion coefficient of the polymer manifests in the apparent self-exchange rate constant for the polymer. So it's like a modified Marcus-Hesch type hopping. And then when you consider the diffusion coefficient of the polymer in this model, which is the blue line, you can see it captures the experimental data quite well. So now that you understand how electrons transport, we want to understand how do the ions transport. And to do that, my group has applied electrochemical quartz crystal microbalance with dissipation monitoring. So in this technique, we measure changes in mass of the electrode while we charge and discharge the polymer. So it's like doing a big mass balance for all you chemical engineers. So if we're going to do a mass balance, we need to think about what is the mass we expect to see. For every coulomb of electrons that transfer, we expect to see a 1.54 milligram change in mass if the anion is a triflate. So that represents some theoretical value, assuming the doping process takes place the way we thought it did. So with QCMD, for time, I'm not going to go into so much detail of the operation, but for QCMD, our raw data is capturing the coupled mass and the viscoelastic properties during charging and discharging of the polymer by measuring the frequency and the dissipation change of the crystal. So in the setup, we have a 3-electrode cell that where the working electrode is the polymer coated on the quartz crystal. And if you're interested in learning how to do this, we've just submitted a review on how to do QCMD for certain in situ measurements. And I hope that'll come out in a month or two. So anyway, so this is our setup, and we're going to be doing cyclic voltammetry. And what we do is we input a triangular voltage wave of different scan rates, so 10, 25, 50, and 100 millivolts per second. The output from our potentiostat is the current. So these two together give you your cyclic voltammogram. We've just plotted it in the time domain. And then the raw data from the QCMD is plotted up here, where we observe the changes in frequency and dissipation. What you'll note is right when we have a redox peak here and here, we have step changes in frequency and dissipation associated with oxidation and reduction. Here's the same data, but instead of plotting it in the time domain, we plot it more in the voltage domain to give you the conventional sense of a cyclic voltammogram. What we see here is these little bumps in the cyclic voltammogram that we can now assign, thanks to QCMD, their physical meaning. So we were thinking that most of the ion transport occurs by anion transport from the doping, but what we discovered in this exercise was that there's actually some lithium cation transport occurring as well, and that's assigned to the lower potential peaks and shoulders. So we'll get into that into a moment, but I do want to mention that when we do viscoelastic modeling of the QCMD data, we can actually get the real-time mass of the electrode to give you a sense of how the mass changes. So there's a general increase in mass as we oxidize the polymer, and then a decrease in mass as we reduce it. And so the majority of the mass transport is the anion going in and out of the film. However, we found that our delta M over Q, that's the mass exchange per electron, was lower than our theoretical value that we anticipated, if we assume it's just a triflate. And so that means something else is transporting. And as I hinted to you, it's the lithium cation is also transporting. So that's kind of coloring or changing the apparent mass exchanged. We also found that this scales with scan rate to the 1/2. I don't have time to get into it, but it is because it is an electron diffusion limited process. To reveal the mechanism of the ion transfer, what we did was we went to a much lower ionic strength to kind of tease out that lower potential peak. So when we go to this really low ionic strength, you're forcing the electrolyte to be in a solvent separated solvent in a highly solvated condition where each ion has this solvation shell that's very well developed. So when we do that, we can clearly see a region of lithium expulsion associated with this first peak. So to take you through this, this graph represents oxidation, where we go from a low potential to a high potential. On the x-axis, this is the current we measured, but we've integrated it so that it represents Q. So as we start to oxidize, the mass of the electrode actually goes down as we're expelling lithium cations, and then it increases as the anions come in. So to give you a view of that, when we have lithium cations expelling, it's because we already have electrolyte in the swollen polymer cathode, and an anion locally dopes the oxide-binding cation, and for balance, the lithium cation has to come out. And then when we go into the anion uptake region, the anion from the bulk electrolyte is coming in. Okay. However, I wanted to point out to you that dissolution is an issue. We see a drift in the frequency, which corresponds to a 14 weight% mass loss. And I don't have time to tell you about it, but I just wanted to indicate to you that this is a common problem for many redox-active polymers. And in other work that we've published, you can solve this issue by simply cross-linking the polymer, and also by adjusting the electrolyte that you choose. So it is a problem that can be solved, and you can see our follow-up publications to this one in which we do that. In my remaining time, I want to kind of take you full circle back to that idea of can we make a battery that is metal-free, addressing these issues with nickel, cobalt, and lithium? Because the work I showed you just before still uses lithium, still uses lithium triflate. In a paper just out a couple weeks ago, we disclosed some design rules for making metal-free aqueous radical polymer batteries. So our motivation for this study was that the radical polymer we're working with could potentially eliminate problems in the cobalt and nickel supply. And then by going to an organic salt, we could eliminate or reduce our dependence on lithium. By using an aqueous electrolyte, we can enhance the safety by eliminating the flammable cyclic and linear carbonates that are in today's current lithium-ion batteries. So we're not the first to think about this idea of the metal-free aqueous battery, but we're some of the first to explore which radical polymer is the best and why. So to answer that question, we explored a series of 3 radical polymers. You can see they all have the tempo group, but they have subtle differences in the linker group, where you have an acrylamide, a vinyl ether, and then this acrylate, methyl acrylate type backbone. So the redox reaction mechanism is going to be largely the same, but we want to understand when we change these subtle things about the backbone, how does it change the performance? What we found is there's huge changes. We first started by measuring the kinetics of each of the polymers in this metal-free aqueous electrolyte. Specifically, the electrolyte is on tetrabutyl ammonium hexafluorophosphate, or I think it's TBAF, sorry, with a BF4. But what we found was that PTAM, the one with the acrylamide, has the fastest kinetics And PTMA, the polymer that we've spent so much time talking about, has the slowest kinetics. We also went on to measure chi and the solubility parameters of these polymers, and we found that PTAM, which has the most favorable water interactions, has the fastest kinetics, and PTMA, which has the least favorable interactions with water, has the slowest kinetics. So there seems to be some link between the water-polymer interaction and the kinetics. When we do EQCMD and we can measure the mass change during the cyclic voltammogram, as we did in the last study, we can see that these water-polymer interactions manifest as hysteresis in the mass transfer. So if you look at this plot with the square boxes, that's the mass change as we oxidize and reduce the polymer. And it's the mass increases because we're doping the polymer and the anion is coming in. PTAM has the least mass hysteresis, and then PTMA has the most mass hysteresis. So this is showing how the sluggish electron transfer kinetics manifest as well in sluggish mass transport kinetics for the polymer. We can also then take that same data, do a mass balance on it, and we can calculate how many water molecules are transferring with the anion. So the anion is a BF4, and PTM, which has really favorable water interactions, only transfers 1 water molecule per anion. So that anion's dragging the water molecule in and out as it dopes and dedopes the film. But PTMA, which has the worst water interactions, drags in a lot more water. And that's explaining why there's such sluggish kinetics and why the hysteresis is so poor, is because you're transporting a lot more physical mass in and out of the electrode. That manifests in really big changes in the discharge capacity. So PTAM, which has the best water interactions, has a discharge capacity of 90 milliamp hours per gram, whereas PTMA, which has the worst water interactions, has a discharge capacity around 75. So this is saying that you can have really large changes in performance by just adjusting the backbone and linker group, where the design criteria now are telling you want to pick a polymer that has favorable polymer-water interactions. And by doing that, the benefit is that you get enhanced kinetics, reduced overall mass of the transporting species, and that gives you improved capacity. So finally, I want to close by talking about our latest work, which came out last week in Nature, about polypeptide organogradical polymer batteries. And this was done in collaboration with Karen Woolley at Texas A&M University. In this project, we designed from first concept, how can we achieve a circular battery lifestyle? Everything I've shown you so far, maybe it's metal-free and it makes you feel good, but we haven't recycled it. And to do that, we need to really think about the polymer, designing the polymer from first principles or first synthesis. So Tan Nguyen and Karen Woolley designed a polypeptide molecule that has redox-active groups hanging off the side that can act as cathodes or anodes. So the idea here is that you can take amino acids, synthesize them into polypeptides and functionalize them with redox-active groups. And then in my group, we assemble them into a battery where the polypeptide is the anode or the cathode, and then we use a metal-free non-aqueous electrolyte to comprise the battery. You could use the battery, and then when you're finished with it, you can add an acid to do acid hydrolysis of the polypeptide backbone. So then it'll degrade into its original amino acid components and other byproducts. And then in principle, if you could separate those degradation products and you could then reorganize them or resynthesize them into, again, the polypeptide anode and cathode. So this is a schematic of the battery where we have the polypeptide cathode and anode. The cathode uses the tempo group hanging off the polypeptide backbone, which we've just talked about in this presentation. And for the anode, we use a viologen. This is the molecular structure, the specific molecular structure of the molecules we have. And we've calculated the theoretical capacities of each of them. So in principle, they can have very high theoretical capacities of 118 to 71 milliamp hours per gram for the viologen and the tempo containing polypeptides, respectively. We assembled them into a full cell. So you can see redox peaks here attributed with the full cell. And we've tested their performance. The full cell capacity, we can achieve about 80% of the full cell capacity in the initial cycles, but with increased cycling, we do see degradation. Again, this is associated with dissolution, which is a common issue for the redox-active polymer batteries. So we can potentially solve this issue with cross-linking the polymer or designing polymers that don't dissolve in the electrolyte. Upon adding an acid, we can identify the degradation byproducts. And we've also done some cell studies for cytocompatibility. You can read about that in the paper. But basically, the battery is dissolving into amino acids and affiliated byproducts. We still haven't had a chance to complete the cycle where we would separate each of these components and reconstitute the polymer. So that would just be my fantasy if we could do that. So I'm going to close now. I'm going to tell you, we talked about the journal, ACS Applied Polymer Materials, but we also talked about some science, the mechanism of electron and ion transport. We talked about solvent and ion. Well, we haven't yet talked about solvent and ion type, but I want you to know those are emerging as key factors in performance. And then we talked about some work where we're getting closer to a fully recyclable battery that's metal-free. And you can keep an eye out for future work because we're still trying. So in closing, I want to thank my group and many of the students who've done fantastic work in this area, our collaborators, and the majority of this work was funded by DOE.